So let's summarize what we know from masses and springs. If I have a spring and I attach it to a mass, and this is the equilibrium position. So when the mass is right here, there's no net force on it. If I pull that mass all the way over to here, the spring exerts a force to the left, which tries to restore this mass to the equilibrium position. And if I were to take the mass and push it to the left, the spring would compress and it would try to exert a force on the mass to the right. So the spring opposes any attempt to displace the mass from equilibrium. Okay, so we say that it's a linear restoring force. And what that means is that the force that the spring exerts is proportional to the distance we stretch it from equilibrium. The farther we stretch it, the greater the force will be. The proportionality constant we call the spring constant. So the way we interpret that is it's the stiffness or the strength of the spring. A bigger spring constant means that for a given displacement, it exerts a greater force. So we call that a linear restoring force. Now, when we have a mass and it's acted on by a linear restoring force and it's displaced from equilibrium and let go, it will oscillate back and forth. That motion is called simple harmonic motion because the graph of that motion is a sine or a cosine function, which are the harmonic functions. Okay, so the period of the oscillation we worked out in class. It's 2 pi times the square root of m over k. And if you want to write an equation that describes the position of this oscillator, then you could do that using a cosine of omega times t, and we'll work on this later, but this constant in here in front of t is actually 2 pi divided by the period. A is the amplitude, and x is the equilibrium position. So we'll work on this part later. Right now, we're interested in this period of the oscillation, okay? So what we found was that the pendulum can also be described by a harmonic function. So in lab, when you guys measured the position versus time of the pendulum, you were able to use a sine or cosine function to perfectly fit it as well. So a pendulum acts as a simple harmonic oscillator, and so we need to figure out why. So let's think about a pendulum. It's a mass attached to a pivot by a string of length L. L is actually the distance from the pivot to the center of the mass. I pull it back some angle theta from equilibrium, so this is the vertical. I pull it back some angle theta, which means that the distance it's going to have to move is s. So s is a typical variable used for an arc length. Okay, and if I let this go, it oscillates back and forth, and its motion can be described by the sines or cosine functions, so it's simple harmonic motion. So let's take a look at the free body diagram. Oh, by the way, this angle here, theta, is the definition of an angle in radians is the arc length divided by the radius of the circle. So in our case, that's L. So theta, the angle, if it's in radians, is the ratio of S, the arc length, divided by L. And that's just the definition of the radians. So if we look at a free body diagram, what are the forces acting on this mass right here? Well, gravity pulls down on it. So that's mg, that's pulling down, and the tension pulls up and to the right at a small angle. Now, this pendulum does not accelerate in this direction. It only accelerates in this direction, so I'm going to call that the x direction. So this is the x direction. So the two forces cancel in the y direction. So this is my y direction, and the forces cancel, and there's an unbalanced force in the x direction, and we're going to call that the restoring force, because it's the unbalanced force acting in this direction which causes the pendulum to swing back this way. So, if we look at the component of this force acting in the x direction, it's mg times the sine of theta. So it's the component over here. It's the opposite side. The component of the force acting in the y direction is mg cosine theta. And that equals the tension, but we don't really care. So what we end up with is an unbalanced force because these two forces are not opposite directions. The unbalanced force is mg times the sine of theta. All right, so we are going to make an approximation. For small angles, this angle theta right here, this angle theta, is approximately equal to the sine of theta. So this is called a small angle approximation. And to kind of show you a little table, here I have the angle in degrees, here I have the angle in radians, and here I have the sine of the angle. So you can see that for 5 degrees, the angle in radians is pretty darn close to the angle in the sine of the angle is very close to the angle. So if we go to 10 degrees or 15 degrees or 20 degrees, you can see that these are still pretty close. The angle in radians and its sine are pretty close together, and I calculated the difference here in percent. So up to about 15 degrees, which is about a quarter of a radian, the angle and the sine of the angle are pretty darn close. They're within 1% of each other. So for small angles, we're going to say that the sine of an angle, which is this, is approximately equal to the angle. So that's going to be our small angle approximation. So if we use that, this restoring force becomes mg times, instead of sine of theta, we can just put theta. So mg theta is the restoring force. That's the component of the force acting in the direction this way towards restoring the pendulum back to equilibrium. All right, now remember theta is the arc length divided by L. So I can put S over L in here for theta. And then I can regroup. I can write mg over L times S. Okay, so what we found is that the restoring force acting on a pendulum is equal to mg over L times the distance it is displaced from equilibrium. S is how far it is displaced from equilibrium. So let's go back and revisit the spring. Remember, the restoring force is equal to K times delta X, where delta X is the distance it's displaced from equilibrium. And when that happens, the period is 2 pi times the square root of m over K. Now think about the pendulum. The restoring force is equal to mg over L times S. So the restoring force, which is this, is equal to some constant, mg over L, times the distance it's displaced from equilibrium. So this delta x and this s are the same thing. It's how far it's displaced from equilibrium. So what that means is that the effective spring constant, the proportionality constant for a pendulum, is mg over L. So for a pendulum, the spring constant, and we put that sort of in quotes, the proportionality constant between the restoring force and the displacement from equilibrium, this proportionality constant, which we call K, is mg over L. All right, so for a pendulum, when you pull it back, there's a force that tries to restore to equilibrium, and the proportionality constant, that force, is proportional to the distance it's displaced from equilibrium. The proportionality constant is mg over L. So what that means is that the period of a pendulum will be 2 pi times the square root of m over K. But for a pendulum, K is mg over L. That's what we showed right here. K is mg over L for a pendulum. So it turns out the masses cancel, and then we have 1 over g over L, which we can just rewrite as L over g. So it turns out that for a pendulum, the period is 2 pi times L over g. The mass cancels. So this is how we find the period of a pendulum. Okay? So let's summarize what we have. For a pendulum, the period is 2 pi times the square root of L over g. This only applies when angles are small. So we're going to say less than about a quarter of a radian or 15 degrees. When it gets bigger than that, the linear restoring force isn't linear anymore, and the motion deviates from harmicity. So we're just going to say 15 degrees. You also notice here that the period does not depend on the mass. So for a pendulum, the period does not depend on the mass. It also does not depend on the amplitude, subject, of course, to the constraint that our amplitude stays less than 15 degrees. You notice that the period is proportional to the square root of the length. So that means that if the length gets 2 times bigger, the period gets the square root of 2 times bigger, or only 1.4 times bigger. If you make the length 4 times bigger, then the square root of 4 is 2, the period doubles. So you have to make the length of a pendulum 4 times bigger in order to double the period. If we were to make a plot of the period on the y-axis and the length on the x-axis, so I want the period on the y-axis, and I graph the square root of the length on the x-axis, then the slope will be 2 pi divided by the square root of g. So I can rewrite this equation as the square root of L over the square root of g. So this would be the slope. And if you work that out, grab your calculator, take 2 times pi divided by the square root of 9.81. You get 2.01 for this. And that's exactly the slope you got in lab when you plotted the period on the y-axis and the square root of the length on the x-axis. So that agrees with their lab. By the way, in lab, we also showed that the period doesn't depend on the mass. It was a horizontal line, and we also showed that was true. So all these connect with what we did in lab. Lastly, the period is inversely proportional to the square root of the gravitational constant. So if the gravitational constant were to get 4 times bigger, the period would get 2 times smaller. The stronger gravity is, the stiffer the spring is, and that means that sort of the imaginary spring, and that means the period gets smaller. So that's our last relationship there. All right, so you're going to solve some problems now with pendulums, and you're going to calculate the period for different pendulums to practice these ideas. Okay, so that's going to be your assignment for today.